So now we need to see what are the limits in x. Well, the region starts when x equals 0, so that's our lower limit. So we need to describe this as x being a function of y, rather than y is a function of x, and that's going to be what?
Y squared.
Yes, x is equal to y squared. Okay. So same integrand dx. So now let's try doing that. So we're integrating e to the y cubed. With respect to x. Well, this actually turns out to be very easy to do. What does it turn out to be?
Then it would just be that times x?
Yeah, you treat y as a constant. I forgot to do dy out here. So we get 0 to 1, so we get x e to the y cubed. Now you're going to plug in the limits, 0 and y squared. But you're going to... So now we'll plug in the limits x equal to y squared and 0. We don't touch the y here. So what we get is 0 to 1, y squared e to the y cubed. And then when we plug in x equals 0, well, we get nothing. So this is all we have left. So now instead of having to integrate e to the y cubed with respect to y, we now have y squared e to the y cubed with respect to y. And how come this one, unlike the other one, is totally doable?
That's the derivative of y cubed.
Yes. So the substitution we make, good old u substitution, y cubed. So du is 3y squared dy. So we're going to get 1/3, and to go from 0 to 1, e to the u du. So finally we get 1/3 e minus 1. Okay. Often, when you have a choice like this, when it's this kind of region, you can just do either one. But once in a while, you get a situation where you get something you just can't integrate, you just switch the order and try that.
Why was it you said that we couldn't integrate e to the y cubed?
There's no integration rule you could possibly use that will allow you to work that out.
Okay.
Yeah. I don't know about e to the y cubed specifically, but one function of considerable interest is e to the y squared. They actually went to trouble of proving that it's impossible. So. Okay.
E to the u, that's the integral.
Oh, it's just e to the u. It's itself.
Okay.
Yeah. So do intermediate step. So this is e to the u 1/3 with the limit 0 and 1 plugged in.
Okay, I see now that's why it's minus 1. Okay.
Yeah, if I'm plugging in e to the 0 is 1.
Right.
Yeah. We've seen region Z can be either type 1 or type 2. What about something that is neither? Okay. Don't bother following the notes, they're not in there. Okay, so here would be an example of a region that cannot be classified as either one. Okay. Now, you can, I guess it's kind of like a mirror image of the top part of a question mark. Okay. Because if you try to bound this by 2 vertical lines, 2 horizontal lines, there's no way, whichever viewpoint you choose, that you can describe your boundaries as functions of x or y. You always have violations of a vertical line test. You can't describe it using a function. So there's lots of regions out there that what I've told you about can't handle. You can try, of course, breaking it up because if you break this up into two regions, so we'll call this entire thing D. If I break this up into D1, D2, you can integrate over D1 and D2 and add the results together. Now, D1 and D2 still do not quite fit that, but you could subdivide as often as you need to. It can be kind of a pain, of course. So, is there something that can be done where you can just take any region in the plane and figure out how to integrate over it, even if it's neither type 1 or type 2? Is there some way to reduce it to integrals that actually can be worked out? And in fact, if that could be done, and you use the integrand f of x y is equal to 1, that just gives you the area of a region. So just in general, that's A of D, that's the area of D. So it'd be a nice problem to solve because that would mean you could compute the area of anything, any two-dimensional shape. So this was actually done. Took long enough, but it was done 20 years ago by an undergraduate student. The idea is this. So something like this. You scan along the boundary from a certain starting point, and here the region's more like a type 1, but as you progress, it eventually becomes more like a type 2. So you place a vertex here. Now you're in type 2 mode for as long as you can be. Place another vertex, and then you're in type 1 mode again for as long as you can get away with it, and so on, until eventually what you have is a polygon. The polygon you can then triangulate. There are numerical methods for integrating functions over any triangle. Then what's left over, if your partition is right, you can handle as an iterated integral. You can define functions here because h1 of y, h2 of y in this case, g1 of x here, g2 of x here. So by coming up with the right polygon, handling a polygon using methods for triangles, and then handling these regions using the appropriate kind of iterated integral, then you can do any region in the plane. So it was the first method for handling an arbitrary region in two-dimensional space. The undergraduate who did that was me. So I'm sure it helped me get into Stanford. So what I wanted to do after that was extend this idea to 3 dimensions. Can you be able to compute the volume of anything in a similar way by partitioning instead of into triangles, approximating by tetrahedrons, and handling the leftover areas by, again, iterated integrals with 3 of them, yes.
So is that called the Langers method or something? Or?
Mathematicians never name methods after themselves.
Oh.
It's just one of those things.
You could be the first.
I would not want to have that distinction.
It's so difficult, like in all his science classes, instead of calling something like
What about?
calling something like a logical name, and he called the author's name.
Yeah.
I mean, it's harder to memorize a name than something that kind of fits what you're talking about.
What about
So what about the people who have names after methods?
Like
So
L'Hopital.
did somebody else give them that name?
Okay, I'll give you a couple examples. For instance, you know about Gaussian elimination, of course.
Yeah.
Yeah.
Gauss-Jordan.
Yes. Gauss had nothing to do with the invention of Gaussian elimination. Somehow his name got attached to it. Maybe he was using it for something. It was actually done. It's been known to have done in China thousands of years